The goal of this component is to try to provide guarantees that can be applied statically that an application is going to operate correctly even before it's begun its execution. This can happen at lots of points in the process, and in our case, we're going to look at whether the application, as it's been deployed onto the physical system, matches what the developer expected. So one way to look at this is by looking at binaries themselves. And there's been a lot of work on this, but since we're talking here about serverless applications, we also want to look at the other steps of the development and deployment process so that we can really cover right up until the application actually executes. So one common solution to ensuring that an application being deployed matches what the developer expected is to use attestation by a trusted execution environment. This can be incorporated into the processor itself, like with Intel TDX, AMD SMP, Intel SGX, and there's also ARM Trust Zone, ARM CCA that are coming out, too many to name here. But fundamentally, these provide some logical link between the developer's binary and the application being deployed. This is great functionality when it's available, but the problem is that large applications are going to be split across multiple physical machines. And this is a problem because it means there is no trusted execution environment, and therefore no hardware-supported attestation, that's able to cover the functionality of the whole application. Just to make things even more complicated, in a serverless application, the application itself may not even know which component is going to be deployed on which physical hardware. So as a result, what we know about the application doesn't necessarily match the real deployment because the attestations of the individual components don't attest the overall structure. They attest individually small parts of the application, but there is no one attestation that covers the whole thing. One solution to this is to come up with a distributed attestation protocol that, before the application executes, makes sure that all of the components of the application have agreement on the identities of each other component, and therefore making sure that the links between different parts of the application are going to be consistent. And so there can be no disagreement over which component is connected to which other component that could lead to the application being incorrectly deployed. We can do this with a consensus protocol where the components agree on public keys and attestations of each component. And by doing so, we can reduce the amount of trust that needs to be placed in the orchestrator because applications can validate themselves that they're correctly deployed and can prove this fact to clients. This component will be integrated into demonstrator 1, but it's also going to be linked with the wider attestation functionality of the Elastic framework, and in particular with the attestation and verification mechanisms which are going to provide the underlying hardware attestations that the protocol requires, but also with the measurement and security orchestration functionality in order to make sure that these components can be connected together in as transparent a manner as possible.
Here is an overview of the protocol before we get into the demo. So first, I would like to explain a few elements of the protocol. Here, the word role is used to describe the role of the components in the application, like a common role can be the database or something along those lines. And it is shared between all instances of a component. And here we have a key pair, which is different for each component, and we use it to differentiate between different instances of one role. I will talk about the other elements as we go through the protocol. So first, well, as it can be seen, we have two TDs running already with IDs 9 and 10. We're going to use those TDs for this demo. Then we start our orchestrator outside of the TD environment. And now we have it listening for the component. Each component runs in one of the TDs. Well, just for simplicity's sake, we will use role names A and B here. Each component and the orchestrator first read the pre-manifest that has our description of the application. In our case, it just specified that this is an application with two components, A and B. And then after that, we start a component with role A and the other component with role B. They each generate their own key pair and then turn the public key into bytes. The key is then, the bytes is then turned into hex and sent over to the orchestrator in that form, and then put into the manifest. And then after that, the manifest is received by both of the components. Well, you can see that the manifest is the same for both components. And then they check, the component checkers, if the roles that are in the manifest match with the pre-manifest. If that is not the case, then it will not consider the manifest a valid manifest and accept it. After that, if it's a valid manifest, they will do an attestation. And in the attestation in report data, they will include both the manifest and the role they are committing to. So when we actually see it in the report data here, it will be different. But in the orchestrator, I have generated the hash of the manifest plus the role for each separate one. So it is as expected, but they're different from each other because they're going to take on different roles. And yes, both of them get the attestation manifest at the end. The attestation manifest can then be sent to a client and be used to make sure the components are as we expected, or we can check it as we did in this case in the orchestrator if they actually agree on the manifest.
So now that you've seen this demo, let's talk about what we plan to have in RP2. So the first thing is we want to tie in with the intra-component analysis, because Wasm components can be built up of many smaller components, and so these then may be linked together during the process of application deployment. And we'd like to analyze these so that we can provide some identification of application behavior, no matter how the orchestrator ends up deploying the application to our platform. Another possible follow-up is to look at how we can do transparent authentication between components using the results of the protocol that we just saw, so that we can avoid having to change applications and to prevent bugs from causing the topology to accidentally deviate from what was attested. We could even combine this with a service mesh to allow the use of this method with hybrid applications that are a combination of Wasm and non-Wasm code, or even fully non-Wasm applications. And then this would increase the impact of the component because we could apply this to general Kubernetes apps.